Welcome to Natural Habitat Adventures Daily Dose of Nature. Today's presentation, Oceans in Motion, How Currents Shape Life on Earth, is brought to you by NatHab Expedition Leader Eleanor Edye. Eleanor earned her undergraduate degree from the University of Winnipeg with a dual major in biology and physical geography. She pursued graduate studies at the University of Alberta, researching tree-line dynamics in the Churchill region, which sparked her specialization in tundra, ecosystems, and bryology. Eleanor, who works extensively in northern and prairie habitats as a NatHab expedition leader, combining her expertise in plant biology and her passion for Arctic and subarctic environments to guide travelers through these unique ecosystems. Thanks for being here today, Eleanor. Take it away.
Thanks, Rob, and thanks to everybody else for being here too. And happy to have so many folks showing up to a webinar where we're going to be looking at pictures of water, talking a little bit about ocean physics, and relating this back to life on Earth. As you can hear in Rob's introduction, I like to focus on small things in life like the mosses, but I also have a tremendous interest in large Earth systems. And I especially think that there's a whole bunch of things that really shape our whole planet, its present, its future, and its past, that many of us have more of a limited knowledge on this than we would ever understand. So again, thanks for showing up, and let's hope to learn something, a new piece of something, a new piece of knowledge about the oceans. I am personally just getting over whatever my kid brought home from school, so if you see me drinking more water than normal, I apologize for the interruptions here and there. It's just to preserve my voice. So we have a lot to talk about today. Going to be starting by talking about why currents happen. What are the driving forces that move water around our planet? And then how do they all relate back to the global system of movement of water and nutrients and energy around Earth? Now, we can't talk about every current because there are some big famous ones, but I do pick two of my favorites to talk about, why they make a big impact on the biological system of Earth. And then something that I think is a really fun bit is talking about currents through time, how they've changed and how they have then changed the Earth's ecosystems as well with that. So to kick us off though, I just wanted to start with a couple of fun animations. And these are done obviously not by me, but by the NASA Scientific Visualization Studio. This first animation is going to be a draining of the oceans, done at intervals of 100 meters at a time. So as we drain the oceans, you can notice, I'll press play here, immediately, pretty much right away, we're exposing the continental shelves, so those shallow areas around our planet's continents. And then we have this gradual drop of the oceans into the deep ocean basins. Most of our oceans go down to around 6,000 meters and no further, so around 18,000 feet. But you'll see that this animation still is not done because those very, very deep ocean trenches, like the Pacific Trench, for example, and the Marianas Trench, goes down to a depth of 10,911 meters, which is over 30,000 feet deep. So I wanted to show this to start out with because it gives us a sense for how our human perception of the oceans is often just us being on top of the ocean or in the top few feet or few meters of the ocean. But really, it's a whole three-dimensional system there underneath the waves and underneath the surface of the water. So the second animation, we'll come to, where are we here? Let's see if we want to go back there. The second animation we're actually going to come to later. So this one was our draining of the oceans. Now, we are going to dive into how currents happen. Ultimately, your take home, your one piece of information to remember about what's driving currents around our planet. Water is moved by a combination of wind, tides, changes in water density, and the rotation of the Earth. Together, these factors give us the surface currents, so the water that is moving in the top 10% or so of our water column, and our deep ocean currents. So wind is the driving force of our surface currents, and wind itself is caused by unequal heating at the Earth's surface. Different things heat up differently quickly. So for example, land has a different thermal mass than water. Land heats up faster and water heats up slower. Just like if you're sitting at the ocean side on a hot day on land, you can feel those cool breezes coming off the ocean. We have unequal heating of the land and the water. As air heats and as that air heats up over the land, heating causes that mass of air to expand and become less dense. So that same number of particles of air is going to take up more space, which means it is lower density. Less dense air will start to rise, and cooler, denser air will start to press in underneath and inward to push that lighter heated air up, and that causes a wind along the surface to be created. So that wind is happening anytime that we have that unequal heating anywhere at the Earth's surface. So over land and water is a common place for unequal heating to happen. But it can also happen on a larger scale, for example, between the equator and poleward. The equator faces more towards the sun. It gets more direct solar heating. It gets more heat being deposited, more heat energy at the equator than at the poles. So we then have high warm air that is going to then be lifted up by cool air moving in, and that air is going to tend to move from high pressure to low pressure until the air pressures are equal. Now that never happens because we're always having differential heating around the Earth's surface. Air pressures are never equal, but where the air pressures are really different, you get stronger winds. When the air pressures are less different, you get less strong winds. And wind, as a term, really we're just talking here about the lateral movement of air, so air moving north, south, east, west. If if air is going up or down, we give it different names like updrafts or downdrafts. So when I'm talking about wind, I'm just talking about air masses moving along the surface of the Earth. Now, if the Earth were static in space, if it were not spinning on its axis, air would tend to move from low pressure at the equator towards the poles where the high pressure is. But the Earth does spin, and as the Earth spins, the air actually is deflected in a certain direction. This is the Coriolis effect. This happens because as the Earth is spinning, the speed is not equal between the poles and the equator. So if you think about how fast the poles are moving, they're really not moving very fast at all, right? Because that is the pivot point around which the Earth is moving. The equator, on the other hand, is moving as fast as you can be on the surface of the Earth, and it's moving at over 1,000 miles per hour. Now, if I'm a mass of air and I'm moving between the poles and the equator, or the equator and the poles, that relative difference in speed is going to affect how I move. If you want to take the air out of the equation, take, for example, this theoretical football player. Let's say it's me. Let's say I'm the best football player ever, and I'm going to throw a football really, really, really hard. And I'm going to throw it all the way from the equator to the North Pole. I'm a really amazing football player. Let's just say that. So as I throw that football, I'm going to be throwing it. I'm lining myself up, and I'm going directly north as I throw my football. And now that football is up in the air, and it's traveling towards the North Pole. But as that football is up in the air, the Earth is actually spinning underneath it. And the path that football takes to head northwards is going to appear to curve with respect to the Earth underneath. this gives us this deflection of air masses around the planet. So when we have air, for example, that's moving polewards from the equator towards the North Pole, it's going to appear to deflect to the right. It does deflect relative to the Earth's surface. And then we have a deflection to the left in the southern hemisphere moving towards the poles. If you've ever heard the urban legend that, you know, if you flush the toilet in the North Hemisphere, you flush the toilet in the South Hemisphere, this Coriolis effect is going to cause your toilet to spin in different directions. That is an urban myth. The Coriolis effect, like what we're talking about here, does not dictate the direction of water movement or air movement in really small systems. It is not a very strong force. However, it does affect large-scale phenomena like air mass movement, like hurricanes, and like ocean currents. So storms, for example, in the Northern Hemisphere will always spin counterclockwise, and storms in the Southern Hemisphere will always spin clockwise. This sets us up for our global circulation pattern. So knowing how this air is moving, and coming up on our next slide here, here's our air movement around our Earth. This is overall going to tell us the direction of our water currents as well. So this here, what we're looking at, we like to call this an ideal Earth, right? If we say there was no land, there was no water, there was no seasonal changes, this is exactly what the planet would look like all the time. But of course, that's not the way it works. However, large trends hold true. If we want to understand the movement of air masses moving around the planet on a small scale, well, that's weather. And weather is really hard to predict because that's talking at very, very small scales, local scales. Like if I want to know whether it's going to rain at my house tomorrow, I'm going to go check the weather app. But this kind of speaking around Coriolis effect can tell us the overall patterns of the way air masses are moving around our planet and the overall patterns of how then wind moves at the ocean's surface. And that is what it has to do with oceans because, like we said, the main driver of surface currents is wind. It's not always exact. Wind will move. So here's our little three-dimensional box here. Wind here is moving away from us. So you can see that big wind arrow at the top left. And that wind is basically going to take the particles of water at the top of the ocean and drag it along with it. So it's providing some of that energy movement to the ocean. As that goes further and further down the water column, those next layers of water are also dragging on the layers underneath them. And there's always a slight deflection in the direction of movement. So our currents are not going to be driven exactly in the same direction as the wind, but they are heading at an angle to that overall pattern of wind direction. And our surface currents, we consider them to be surface currents down to around 400 meters or just over 1,000 feet. And that really marks the kind of depth at which oceans are affected by direct winds, and therefore by the friction movement between the water particles. So there are our surface currents. They're driven by wind, they're driven by water particles pulling on the water particles that they're around and driven by the friction and energy in the system. And that pattern of movement of air around our planet, and then those winds dragging the water along with it, gives us this pattern that we can see here of surface currents. So if you look at them here, these currents are marked off in different colors based on whether or not they are a warm current or a cold current. And all that really means is this water moving from the equator towards the poles or the poles towards the equator? Because we get more solar energy at the equator, the water is going to be warmer. As it moves away from the equator, it's bringing that heat mass with it. If it's coming from the poles going towards the equator, it is a cold water current. And in this image here, the black ones are kind of equitemperature currents. So not moving any big amounts of energy around. So here's my next animation that I was waiting for. And this is an animation, again, from the NASA studio here, of the surface currents actually being shown around our planet as they are moving. How cool is that? I think it's so neat. So it's just a continuous loop, really, of those surface currents of Earth. You can see there's a lot of movement right along the equator, but there's also currents that are set up moving in those big cells like we saw in the last image. So let's just bring up another picture here. There we go. Back to our ocean currents. So the other thing that is formed by these currents are actually large systems called gyres. So gyre is a system of rotating ocean currents. Again, these are just surface currents that we're talking about, and they are rotating at that top 400 meters or so of the water column. And if I take, for example, the North Atlantic gyre, I can see that warm water is leaving the equatorial areas. It is heading up along the east coast of North America. It is cooling off in the North Atlantic, and then it is coming back down south through the Canary Current there. And then it is essentially making this big old loop around this gyre. Now, those currents that you can see there, you may not be able to see the names. Many of them do have proper names. Those are large sustained currents like the Gulf Stream, like the Canary Currents, like the South Equatorial Currents that do go by proper names. But all of those still form these large ocean system gyres. And around our oceans, we have 5 major gyres: the North and South Pacific subtropical gyres, the North and South Atlantic subtropical gyres, and the Indian Ocean subtropical gyre. And then there are some much smaller ones as well, but these are our 5 major ones. Now, before we even start talking about like whole ocean systems and currents at depth, gyres all by themselves are pretty important biologically. And a really good example of how gyres are important is because they are where things tend to end up. So those ocean currents tend to direct things inwards towards that path, while at the center of the gyre, there's often very little in terms of current and little in terms of wind. So if you've ever heard of things like, for example, the Great Pacific Garbage Patch, that is not one singular mat of garbage, but it is the central part of the Pacific Gyre, where ocean currents are not, they're tending to bring things inwards instead of moving things outwards. So it's just a higher density of floating plastic garbage in the North Pacific Gyre. But for biological reasons, there's other really interesting gyres. For example, the Sargasso Sea. This is an ocean gyre in the Atlantic Ocean that is still bounded by those 4 currents in the North Atlantic Gyre. And it's kind of interesting because it's the only named sea that actually does not have land boundaries that define it. It is the location of the currents that defines where this sea is. And it's distinguished biologically from other parts of the Atlantic Ocean by the fact that it is just absolutely full of the sargassum seaweed from which it gets its name, the Sargasso Sea. So this was an area that early explorers knew about. They knew that there were very few currents, that there was no wind, that it was a terrible place to get stuck, and that they were concerned that these big masses of floating seaweed would stop them from being able to visualize like beaches or rocks, any kind of hazards in the water. But these floating mats of sargassum seaweed are actually really important biological areas for over 100 different species of animals that are supported on them. For example, there are a whole bunch of fish that live there and reside within the seaweed for parts of their life cycles. Young sea turtles spend time there as well. Some other marine organisms do too. And that has ended up being, by the fact that it's bounded by these currents, it is all by itself a really important biological area. So cool stuff can happen with currents. There's some nice flat floating mats of sargassum seaweed for you. Okay, so those are our gyres. Now, I always like to ask the question, like, how do we know about this stuff? How have we learned about ocean currents? Well, we've known about this basically for as long as we've had sailing ships, right? Sailors have always noticed differences in winds at different latitudes. So areas around the equator that tend to have like very still air because of the low pressure area, call them the doldrums because there were no winds and you couldn't go anywhere. The horse latitudes are another area of pressure convergence where there tends to not be a whole bunch of wind. So if you're a sailor and you're trying to, you know, make your way across the ocean, finding yourself in the direction of the area of the trade winds, for example, was a good choice because there's pretty reliable winds in that area. And we also know that now those winds derive those currents. And really, we've known about surface currents for a very, very, very long time. We have had accurate ocean current maps since the late 19th century. They have been tracking patterns of surface currents. Like I said, as soon as we got the sextants and we were able to say what longitude we were at, people were making recordings of where these currents were and making sure that they knew about it, because that helped you to get home safely and it helped you to maybe not get stuck in the middle of the ocean without enough water because you were in the wrong spot without any currents that would carry you home. So I think that's pretty cool how long we've known about this kind of stuff. And in fact, by the 1830s, we had pretty well all of the non-polar currents accurately charted. So lots of knowledge here. But there's also other fun ways that we know about surface currents. It's not like we're not monitoring them anymore. Things like surface temperature sampling, sampling of phytoplankton, so the living organisms within the surface. These are often like long-term ongoing scientific studies. Many of them are done in conjunction with merchant ships and like shipping organizations to collect data as they are moving goods around the earth. One project, for example, with the Department of Fisheries and Oceans in Canada was using drift bottles to study ocean currents. And drift bottles are just a very low-tech way of studying ocean currents. You basically put a note inside a glass bottle, you stopper it up with a watertight lid, and you put about 25 bottles at a time or up to a couple hundred in the ocean, and then you track where they reappear. These bottles all have writing on the sides that say break this bottle, so that you know to break it and look for the instructions inside. With this tracking, about 1 in every 25 bottles are found, and they are used to help track where the surface currents are actually moving things around. Because while we might know kind of the overall pattern of the currents, it's really helpful to have better information, more data, better modeling for, like, ultimately, if something were to be dropped in the ocean right here, where would that thing end up? And if that thing is, for example, an oil spill, if that thing is a spill of like radioactive pellets, if that spill is, right, if that spill is a lost human, where are the patterns of where that item might end up? And things like bottle drops are still being used for that. If you find yourself like really intrigued by ocean currents, I can recommend an oldie but a goodie book called Moby Duck. And Moby Duck is all about this spill, this terrible spill of bath toys that happened in 1992. And depending what you were doing in 1992, you might even remember this. So this happened in the North Pacific. A container of these floaties, that was the name of these floating plastic animals, was washed overboard, and there were 28,800 of these things that were basically dumped in the North Pacific. They took one of those 4 forms as shown on that guy's arm there, and unlike other bath toys, this is the important thing about the floaties, they did not have any holes in them. So if you've ever had, you know, a floating duck or a rubber duck, they usually have that little thing that you can squeeze to expel water. Friendly floaties did not, so they would presumably float forever and ever and ever. Oceanographers actually tracked their progress, and the recovery rate, like I said, it's around, like, it's quite low, it's about 2%, so less than 1 out of every 25. And they were able to collect up a number of these floating plastic animals at these spaces that you can see here in the map. So from their original location in the North Pacific, some of them ended up in Indonesia, some of them ended up in Australia. One of them, or at least some of them, went up through the pack ice across the North Pole and through the Polar Sea and ended up in Scotland and England, and then onto the east coast of North America. And I think it's a lovely way to kind of, not only is it like a fun accidental experiment, but it's a neat way of like reminding us of how much, even at just the surface, our oceans are really connected. Cool. Okay, so that is our surface current. But let's go global, because remember, our ocean is 3D. Just like we saw in the beginning of with that video, there's a lot of underwater topography. So our surface water movement is driven by wind and to some extent by tides. But here's where we're going to make it 3D and go into the deep ocean, because deep ocean currents, we already said they can't be driven by wind because wind does not go down that far. Tides are not having an impact at that depth either. Deep ocean currents are driven by density changes in seawater. So if we track these currents here are the colors on this map. They're not warm and cold, they're surface and depth. So red color marks the surface movement of water. So here we can track the Gulf Stream that we'll talk about in a minute up the east coast of North America. It comes to these places here of deep water formation where that water is going to subside. So it's going to move down in the ocean column, and it's going to travel along the depth, so towards the bottom of the sea, moving kind of downwards towards Antarctica, where it's going to join up with the surface system again. And this is a global system where the speed of movement is, it moves the water around about a few centimeters per second. That actually seems kind of fast to me, but when you think about it, if you placed a random drop of water somewhere along that global conveyor belt, and you said, how long would it take for that single drop of water to make itself back to that same location? It would take about 1,000 years for that water to follow that entire path of global circulation like that. So this global conveyor belt is a huge, huge part. Like, it is the driver behind moving heat around our planet, in moving salt around the oceans, and in moving nutrients around the ocean as well, that are required for plants and other organisms to live in. And this whole thing is driven by density differences and downwelling of that water, because what's actually happening to move that water down? I said the water goes up towards the pole and then it sinks. Well, why does it sink? It is those density differences. So water is less dense as it gets warm, right? So as water warms up, it takes up more space. It is a lower density. But water is pretty unique in that its most dense temperature is actually usually above the freezing point. So fresh water is most dense around 4 degrees Celsius. So if you were to go out to a lake, for example, and you came to the most dense water at the bottom of that lake, it's going to be sitting around 4 Celsius. But seawater will not freeze until it reaches points of -2, so around 28 Fahrenheit or even below, depending on the salinity. And that's where it is most dense. So if we're following our surface current, so here's our surface current, it's leaving the equator, it's going towards the poles. Let's say this one's going to Antarctica. So it's traveling, it's moving all of that warm water going southwards towards the South Pole. So as it's traveling, it's cooling down, it's cooling down, it's cooling down. And as it cools, the density starts to increase. And it cools and it cools and it cools. And as it cools far enough, because it's moving towards some very cold areas of the planet, it's going to start to reach the freezing point. And ice will form. Now, ice is really not salty ice. It's just frozen water. As it freezes, it leaves behind, or it rejects, the majority of the salt in the water around it. As that ice gets pulled out of the water, and it's now ice, the water that's left behind is now even colder and even saltier. That water is now the water that's going to sink down. And that sinking and therefore it's pulling in water behind it and displacing other water as it sinks. That sinking of the water is what is driving that whole conveyor belt around our planet. The process is a little bit different in the northern hemisphere. It's driven more so by evaporation instead of by freezing. But it is like, it requires that temperature gradient, it requires a cold pole, and it needs that cold, salty water to sink down and pull other water in behind it to start that conveyor belt. So just to look at it one more time here, so you can fully appreciate it. So those yellow circles there that you can see on the map, those are the deep water areas. So that is where our water is leaving the surface and heading down towards the bottom. It's just, I think it's really cool. So there's really two parts to it, right? There's a northern hemisphere part and the southern hemisphere part. There's the Atlantic overturning system, and then there's a Southern Ocean system, but they are connected up, but they also kind of do their own thing on their own too. We know more about the North Atlantic because that's where more people live, but these are both connected yet independent systems to move all of this water, this energy, these nutrients around our planet. And if you were to look at it kind of in a cross section here through the entirety of the Atlantic, you can see that the movement of the water is very different depending on what we're talking about. And that sinking in the North Atlantic and that sinking in the Southern Ocean actually creates these deep water areas where the Antarctic deep water is actually even colder than the North Atlantic deep water. And so it creates the stratification, these layers within our ocean. So overall, really cool. This whole ocean circulation, right? It depends on the wind to move things, but the only thing that moves the deep layers of ocean depends on those density differences. You need that cold, salty water to make this whole thing the 3D system that it is. Now, how do we even know this? How have we learned this? Well, remember I said that we learned about surface currents, and we had a really good understanding of them back by the mid 1800s. Even at that point, they understood what the following was because of their understanding of chemistry and physics, right? Once you know your water is getting colder and saltier, you know that water is going to sink, you know it's going to be moving the water underneath as well. But we also know about it through programs like the Argo probes and the Argo array. So these are ocean probes. There is about 4,000 drifting Argo floats around our planet, and they are constantly tracking sea temperature, sea saltiness, and then some of the newer ones, they're also tracking things like biological activity, chlorophyll levels, the amount of oxygen, the amount of plankton in the area, the pH of the water. And these are super cool probes. They're deployed, as you can see, all around our oceans. And they just hover around 3,000 feet down in the ocean. And every 10 days, they dive down to about 6,000 feet, and then they come up to the sea surface. They broadcast their data via satellite, and then they sink back down to the 1,000 meter mark, so around 3,000 feet. And these have been up now for a couple of decades at this point. So we have a lot of great information from the Argo program. This is one of many projects that we have to study and better understand our oceans. This is, however, like the main global one that we use for tracking global systems. And we use it to predict a lot of things, including whether or not it's going to be an El Nino year or a La Nina year. So the El Nino is the high temperature phase of the El Nino Southern Oscillation System, where we can kind of determine what global patterns are going to exist based on the patterns of sea surface temperature in the Pacific, for example. So I think many of us have been impacted by El Nino or La Nina at some point. We know about this and we can predict it in advance thanks to probes like the Argo. Now, I promised that I would talk about famous currents, and I picked my favorite two. You may have other favorites, but these are my favorites, and I think they are probably the best known currents as well. And they are the best known currents because they affect humans, right? They impact our lives and how we move and how we live. And the first one I want to talk about is the Gulf Stream. So as we talked about currents and the movement of water, I also said that we're not just moving water, right? As we move that water contains energy because if it's moving heat around, it's containing energy. It contains salt. Sometimes it has ships on it as well. Sometimes it has little rubber ducks in it, but it's also moving nutrients around our planet. So critical nutrients, same things you add to your garden like nitrogen and phosphorus and potassium, are needed by plants like phytoplankton, who then get eaten by little bugs, who then get eaten by fish, who then get eaten by dolphins. And all of those nutrients have to cycle around the ocean as well, because nutrients can't really be used up. They can get recycled, but they can end up in ways or in places that they aren't very helpful to those organisms that need them. So if my nutrients are in the form of, dolphin poop, that might not be very helpful to me if I am a fish. I'm not out there to eat dolphin poop. If my nutrients are in the form of a dead piece of kelp, that also might not be something that any particular organism wants to eat. So as those nutrients things die or get pooped out, they move downwards and they end up in the deep and then get shuffled around again by our conveyor belt. So the Gulf Stream is a named surface current, but it is also part of our larger global conveyor belt system where it's moving water and moving energy around the planet. Now, we as humans notice the Gulf Stream mainly because of its influence on temperatures, particularly air temperatures. So here are some January temperatures. And if I were to pick a line, I'm going to pick, say, 58 degrees north, which is the latitude of both kind of central Norway and central Canada. I see in central Canada deep, deep blue, which is a temperature of -20 or colder. Yay. If I move over to Europe, you can see that same latitude brings me a much, much warmer temperature, even with an average January temperature of close to freezing, which is why, thanks to the Gulf Stream, here in Manitoba, we get polar bears growing at that latitude, whereas in Norway, they have been successful at cultivating palm trees at that latitude. It's not that it's inherently warmer or colder in east or west, it's that the Gulf Stream is moving that warm equatorial water along the east coast of North America and over towards Europe. And it warms up Iceland and it warms up Europe, and it keeps everything there quite a bit warmer than it is at a similar latitude in North America. Oh, Gulf Stream. Sometimes I want to be warm in Canada too. So, like I said, the water's moving salt and heat and nutrients, and then these currents that we're talking about are also, so here's our wind moving across the surface. It's moving our currents along, our surface currents along as well. And as water gets pulled out of an area, upwelling can happen in areas where we have deep ocean water moving upwards, especially where deep ocean water is hitting some kind of natural rise, like the edge of a coast, for example. These areas of upwelling are really important. They are driven by wind and therefore currents to areas where the water is moving out, and then nutrients get to come up and replace other areas here. So this map here is highlighting major upwelling areas, and you can see here that these are mostly along the world's coasts. So again, this upwelling is happening when water is at a depth, which is a higher nutrient water, gets pulled up because the winds are blowing water away, and water gets pulled up along the coastal areas like that to replace the surface water. So these waters are usually colder, they're rich in nutrients, and they give us very biologically productive areas. These are areas that are well known as good fishing grounds. They're usually areas that are well known as just high places of biological diversity. And if you were to take this map out of my head and you asked me, like, if I had to guess, and you're like, Eleanor, tell me all the places where upwelling happens, I'd be like, oh, I can't remember the map. But if I were to guess, it would be anywhere that we see high levels of, for example, fishing by humans or fishing by other organisms like dolphins and whales, where there's high amounts of biological productivity, where baleen whales show up in the summer or winter months to come feed off of this high productive areas. And I want to take us for a second here back to Iceland. You can see I put a little star around that. You can see that Iceland is also a high productivity area because of that upwelling. And that Iceland also sits at kind of a joining point of a number of different currents. So we have a lot of water moving around the area. Iceland represents a pretty sharp rise in the height of the seafloor, and it's a great place for upwelling to happen, for nutrients to be available. And in fact, it has been a place known not just to humans, but of course to all the other organisms that also use upwelling for a long, long time. So Iceland has been one of the major Atlantic puffin nesting grounds, with fossil evidence of puffin use going back over 2 million years. So puffins do not spend their entire year in Iceland. In the winter, they are in the open ocean, they are in the North Atlantic, but they're coming back to places like Iceland in breeding time because they need cliffs with appropriate land for their nesting burrows to lay their eggs in and raise their chicks in. But along with needing that location to actually lay their eggs, they also need to be close enough to an adequate supply of nearby food. And for puffins, that's especially around Iceland, that is a species called the sand lance. We have seen in Iceland warming ocean waters, as we have seen those, like the Gulf Stream, bringing more and more heat. It is actually starting to warm the ocean waters up around Iceland, and it is reducing the availability of their food, like sand lance, because sand lance can only survive and thrive in cold ocean water. They like the ocean upwelling, they like all that nutrient, they like all of the phytoplankton in the area, but if it warms up too much, the sand lance can't make it. And the warmer it gets around places like Iceland, the further and further those puffins need to fly to get their food, to bring it back to where their chicks are. And that costs them more in calories for themselves. And if you've ever seen a puffin fly, they're not really good at flying. So adding to their distance is a real threat to them, as that Gulf Stream, brings more of that hot water up towards Iceland. The other famous current I want to talk about is the Humboldt Current. And I know that there was a webinar earlier this week about the Galapagos. So if you attended that, you may have already heard the words Humboldt Current, or maybe you've already visited there. The Humboldt Current is the current that runs from the South Pole region, so from the pole towards the equator along the west coast of South America. And as it kind of gets towards Ecuador, it moves following that same kind of global pattern we talked about, where it's forming a gyre. It's turning towards the west, and it comes up and interacts with the Galapagos Islands. And it is that current that really gives us this really oddly productive area, where the islands themselves are often quite desert-like and have very low amounts of precipitation. These volcanic islands that just have this abundance of species on and around them. But if we look again at our little upwelling map on the bottom left there, you can see that that is in fact an area with a lot of upwelling. And if we were to take it to the human side as well, like I said, if people fish there, it is probably an area with a lot of upwelling. And this map on the right-hand side, the darker the red, essentially, the more fish we are pulling from the ocean in those places. And the western side of South America is a very, very, very productive area because of the Humboldt Current. Cold water with lots of nutrients hitting the edge of the continent and getting that nutrient pushed up, creates an area with a lot of productivity. So here we have the equatorial current. It hits the areas around the west coast of South America, including the Galapagos Islands. That cold, nutrient-rich water gets pushed up, and it's basically like dumping fertilizer into the ocean. And then all the plants can grow, and then all the things that eat the plants can eat the plants, and then you get, penguins and whales and all the fun stuff around. And then all of that surface water then gets pushed along with the surface current there. Okay, cool, fun. However, the Humboldt Current and the amount of water that moves around in the Galapagos and along the west coast of South America is not a static thing. This is the area in which we can see some of the biggest impacts from the La Nina, El Nino cyclings, or the Enso cycle. When those trade winds that push the water across the surface start to die down and they weaken, the current that like draws all of that nutrient in the Humboldt current can weaken, and sometimes things can actually reverse a little bit. So warm water starts to accumulate, the temperature starts to increase, nutrient cycling basically stops or is very decreased, and we see some very, very different patterns of life in those areas. And sometimes those currents change. And when we have Galapagos cycling, when we have the Humboldt current not doing what the Humboldt current usually does, we see big, big, big impacts in what happens in areas along the south coast, the west coast of South America, and the Galapagos Islands. So I wanted to pick out those two currents because I think they're good examples of currents that we interact with either on a daily basis if you live somewhere affected by the Gulf Stream, or if you know about the Galapagos, or if you eat fish, if you ever eat Chilean sea bass, you've been impacted by the Humboldt current. But those currents, right, are not static. They change over time. The Gulf Stream can get warmer, the Humboldt current can weaken, and we see year-by-year fluctuations in these currents that impact human life and life on Earth. Then if we want to take it another step back again, we can talk about ocean currents in the past. And we're going to go real far back and say, well, okay, so now that we know currents can change year to year and that overall patterns can even change, things can weaken, things can strengthen, more heat can be carried or less heat can be carried. Does that mean that as the Earth has gone through all of its changes over the millions and millions of years that it has existed, have the ocean currents always had the same pattern? And the answer is absolutely no. It's been like real wild out there sometimes. And I want to take us back to Pangea, so around 200 million years ago. If you watch some of my other webinars, you might remember Pangea is a time not so great life conditions on Earth. A lot of things died. A lot of life in the ocean died, a lot of life on land died, big mass extinction. Not a great time to be an animal or a plant on this world. If we look at the patterns of ocean circulation at this time, like obviously we're extrapolating here, but we have a pretty good idea of like the physics and the chemistry of how this works. We think the biggest change here would have been that while there was still ocean circulation in approximately the same patterns that we have now, the biggest change would have been that there were no spots where deep water formation could happen. Because while there were like enough density differences to drive like overall surface and mid-level circulation, we don't think that there was enough of a density difference to drive deep ocean and deep water circulation. So the water sitting at the bottom of the oceans would have been quite stagnant. It would have been anoxic, meaning that there was no oxygen available at those low levels. It was probably very high in hydrogen sulfide, and it was also very low in pH, so very acidic water too. Together, this was one of the drivers of the big extinctions that happened at this time, was that there was no oxygen reaching down to the lower levels of the ocean. So just by like as we change ocean circulation, it can have huge, huge impacts on life. Let me give you a more recent example, because it's only been about 3 million years that North America and South America have been joined by the Isthmus of Panama. And the joining of that isthmus had a huge impact on our climate systems on Earth and the overall environments that humans got to evolve into. So before Panama formed, and it was done through a series of volcanic eruptions over several million years, we had a flow of water from the North Pacific into the Atlantic. We had things like puffins were one single species. They moved back and forth in between. The seaway was open, water flowed, energy flowed, and there was overall exchange of water between these two big ocean basins. But 3 million years ago, that seaway closed. And the closure of that seaway is what ended up creating our modern Gulf Stream. Before this time, we did not have this kind of unequal distribution of heat moving along the east coast of North America and then over towards Europe, because there was simply circulation moving kind of through what's now the Isthmus of Panama. This amount of hot, salty water moving from the equatorial areas going northwards was likely one of the main drivers of the Ice Age that started just a couple thousand years after the Isthmus of Panama formed. It's probably not the only driver, but it is absolutely a main driver, because now you have all that hot, salty water. It's bringing all of that energy going northwards, and that creates more energy, makes more clouds, makes more precipitation. And when that precipitation is falling as snow, you get that quick buildup of ice caps and ice sheets. So just changing the way the water moved basically threw us into an ice age. Let me tell you another event. This is even more recent than this. This is around 10,000 years ago. And this is actually where I live. So this is North America. There's Hudson Bay. And Lake Agassiz was a meltwater lake formed by the Laurentide ice sheet starting to degrade and melt out. Beautiful lake. Every time I drive home, I get to drive up the old lake shore over the escarpment where the side of the Lake Agassiz used to be. Now, Lake Agassiz was there for a very long time. It was there the whole time that the ice sheet was melting, in greater or lesser extent. But what evidence tells us is that Lake Agassiz drained very rapidly. So at some point, the Laurentide ice sheet just gave out, and there was a massive flood event where the entirety, or almost the entirety, of Lake Agassiz drained out in a matter of weeks or months. Wow, that is a crazy disruption to a global system. So all of that fresh, relatively warm water just all of a sudden drained out into the Atlantic Ocean. And what it looks like that did is temporarily shut down that deep water system again. So we had stagnant fresh water, so less dense water, sitting on the North Atlantic that was then not able to sink and overturn the entire global circulation chain there, the North Atlantic deep water production. And essentially the whole system shut down. The Gulf Stream basically stopped moving, and we had a sudden return to cold conditions for about 1,000 years. It happened really quickly. The temperatures dropped about 10 degrees Celsius over the period of a human lifespan. So over about 75 years, they dropped 10 C on average. We call this the Little Ice Age. And then over time, circulation was able to reestablish itself around 1,000 years later. That North Atlantic deep water circulation was able to start back up again. And we just kind of went whoop right back onto the same path that we were on, where things just popped right back out of the ice age that was temporary. And I will just leave you with kind of where we are right now with the North Atlantic deep water. Oops, one slide too far. And talk about the future. So what we have noticed using the Argo probes and a lot of other studies is that the North Atlantic deep water and the Antarctic bottom water transport has been weakening over the last couple of decades. We think that this is because of increased melting from, for example, the Greenland ice sheets and the Antarctic ice sheets that is then putting a lot more fresh water into the system that is stopping that deep water from forming. So we're looking here at side B, where we have the ice melting off of Greenland. We have this pooled fresh water basically halting the thermohaline or the global conveyor belt circulation because we don't have that ice being formed. We don't have that dense water sitting on top, pulling that water down. And this is going to be the real interesting thing. That the caveat is that, like, we think that the collapse of this circulation is probably more than 100 years away. And it probably won't even happen unless we don't slow down our carbon emissions. But this is kind of the projections that we're looking at, is that even if we are on a global climate warming trend, that if we continue to warm fast enough, dumping all that fresh water into the North Atlantic and into the Southern Oceans may actually slow down global circulation to the point that the pole areas cool down rapidly and significantly while the equator heats back up for possibly 1,000 years until that circulation is able to reestablish. So you don't get any more big picture than that. It's the kind of thing that is important to think about, that I like introducing people to. And humans have a hard time thinking in terms of whole Earth systems sometimes. I know I've taken things pretty close to the top of the hour here, but I'll turn it over to Rob for any questions. In the meantime, I hope you've learned something and can appreciate maybe the mysteries of the ocean maybe just a little bit more now.
Eleanor, thank you so much. So we do have just a little bit of time for questions. So if you do have questions, please feel free to submit them via the question field in your control panel. That's the 3 lines on the upper right-hand corner. You really have done a great job of actually tackling most of the questions as you went on, which is the benefit to going a little bit longer. So I think we've really covered everything. So if you have any closing comments for us, Eleanor, please feel free.
Wow, I'm just impressed at myself here. I'm answering all the questions before I can even be asked them. So with that, I'd just like to thank everybody for coming by today. I know that when we talk about whole Earth systems, they are big and sometimes a little slippery to grasp. But I love to look at these because I think that they are very understandable to all of us, and thinking in ways that things have changed in the past and can also change in the future are always so valuable. And I, again, just thank you for coming and listening today.
Eleanor, thank you so much for taking the time to present this for us today. And I'd also like to thank everyone who joined us. So if you are interested in information on how you can travel with NatHab, please give us a call at 800-543-8917, or you can send us an email at info@nathab.com. Our adventure specialists are happy to help you out. So join us tomorrow, please, for our next Daily Dose of Nature. You can check out this week's lineup, including our registration links, on the website at nathab.com/webinars. We did record today's presentation, and we will have the replay available on our website soon. With that, I will conclude today's webinar. So long, everybody. We'll see you next time.